So, good afternoon, everyone. Respected delegation, and thanks for giving this opportunity to share some of the thoughts related to the newly coming product. I'm going to talk about a specific product, not about which is based on the cloud applications and all. So, the name of the product which I'm going to discuss about is the related to the well construction part, which is the real-time well engineering, which is also called as a RTV. And RTV is based on the data in the real time which is coming from the rig, and it is ingested into the model, and from the model we get the interpretation of the different drilling dynamics. So what exactly I'm going to talk about the first, what is the real-time well engineering, and followed by the overview of the what is the data flow of this real-time well engineering model, how the data flows from the rig side to the model and does the further interpretation, followed by like what are the different types of modules in the RTV. So there are two different types, which are the engineering models and some of them are the scientific models. So engineering model is like there are some models which are already exist in the industry. There are some enhancements in this engineering in the back end side of the mathematical calculations. Plus we have the science-based models. And I'm going to talk briefly about each model accordingly and what is the future roadmap or the real-time engineering, how it is going to be and in the progress and how it will be across the globe within the 2 to 5 years time. So this is again, if you say the real-time well engineering, it is a cloud-based applications. So it is a cloud-based, but it can be on-prem as well. So there is a facility that you can do. It's a on-prem installations, and you get the real-time data from the rig, or it can be a cloud-based. You can put your data on the cloud. And then what exactly it does is automatically detects the rig states, and it couples the engineering system along with whatever the uncertainties are present in the data. The models, the mathematical models will compute, and those computations will give you the probabilistic results. So more probabilistic, you can actually trust on the interpretation part of the what model is delivering. And also it also automates the ENP workflow of the client. Like client have their own workflows. They have the set of the process which they are following. So what RTV does is align with those process and add more engineering and mathematical solutions to those models. And it is also supported by the AI and ML technologies there. So what it does, what is help actually, it is actually enhancing your well constructions or well designing, and helps in those processes to enhance, gives the more probabilistic results. And also it helps you to give more time spending on the valuable decision making thing, rather than thinking about how the process will be. So it will take you to closer to making the valuable decisions at the real time, and at the same so that you can reduce the cost, reduce the NPT. You don't want anything to happen just randomly. So you spend more time in decision making, so that you take a right decision at the right time. And also it helps in your increasing the proficiency, decreasing the uncertainties of the computations. And also you can integrate those systems into the different connectors with the client side, so client or the user side. So you have the different users with the different type of the systems. You can have a connector built in, and you can plug in those connectors to get into the client systems. So this is how the data flow happens from the RTV side. So you have the different systems available on the rig side, like a mud logging systems. You have a directional drilling systems, LWD type of the data, and this type of data you can get it into the systems where you can set up those data. You can do the QC systems, and you can transfer that data set right from the rig side to the RTS, through the RTS systems, and you can consume that data into your real-time well engineering systems. So all this data which is coming, it comes into the synchronizers, and from the synchronizers it comes to the real-time well engineering systems in the different models for the interpretation. So what are the different type of the models which I just talked about? We have engineering models and we have a science-based models. So engineering models are some of the conventional models like a torque and drag, hydraulics. Those are already existing in the industry. Anti-collision systems, while monitoring the anti-collision between the different wells when they are approaching to each other. And other things what it does is about the well intelligence. So well intelligence system, I'm going to talk about it. And also you have some ROP optimization done, and also some of the KPI, key performance indicator monitoring, which is like a streaming analytics. So those are the engineering models which are present. Apart from the engineering models, there are some of the scientific models which are available with these systems, which includes your advanced bit wear prediction. So like when you are running in hole the bit and the prediction of the bit, when it can wear, the estimated, the probabilistic path to actually calculate the bit wear, that is also included in this model. Second one we say is about early kick and loss prediction. Early means like it is the kick and loss prediction, but a little bit early in early time, so that user or the rig system can take the necessary decision at the same time. Third one is like a trip map indicator. So like we do the tripping in, tripping out, I mean pull out a hole or running in hole, but what happens, like we don't know what is the condition downhole happening. Let's say you are stop the flow, if you have a static condition, you are pulling out a hole, what are the indicators you have? It is like your hook loads and all when you are seeing. Before you are getting stuck, it might give you some indications, but it can get suddenly stuck. So trip map indicator is basically the mathematical model working in the back end, which includes some of the hook load related, drag related, friction factor related information taken into consideration. And it's when you start trip out of hole, it gives indications that at different depths or the different trajectory-wise positions or location, how the whole condition is, whether it is good, bad, severe, critical, do you have to stop it over there? So that condition it predicts. It's again, it's a probabilistic model. So it helps you to take some decisions. So you are not blind at that point. You have some data. You have some, you know, the parameters which are the indicators for all those trips. And swab and surge. Swab and surge is, as we know, like swab and surge happens while trip in and trip out of hole. But this swab and surge will give you the optimum speed of the tripping in or tripping out of hole, which is in the back-end computations. So when you trip in or trip out, it gives the optimized speed, which will help you to reduce the problems which will be related to your, you know, crossing the fracture gradients or getting fracture at the shoe or in the formation. So that can be reduced, or that can give you the, you know, advanced information to stop that thing. And after all, we have the last is the stuck pipe avoidance model. The stuck pipe avoidance is the, I mean, stuck pipe is the major challenge all over the world. We are facing a lot of problems with stuck pipe in any type of the formation. It could be because of the formation pressures. It could be because of your bad practices. It could be because of the rig limitations or the humans which are incapable of understanding the problems. So this model will assist to do more prediction about the stuck pipe. So the stuck pipe models, which includes the like you have a pack of indicators, you have casing runnability, you have plug friction factors, and you have cutting bed indicators, and one major one is about the casing runnability, which we are actually testing as a pilot project across a couple of the companies across the world. So this is, everything is about, again, the same models, how we can do it. I would like to show the ROP optimization is what basically, it gives you the window, the safe drilling window in between the lateral, torsional and the ROP line. So lateral vibration, torsional vibrations and ROP line. In between that, you can have your RPM and weight on bit kept over there, and then it indicates the safe drilling window all the time. So if you go beyond the safe drilling window, you might face some of the vibration related problem. So that's what this model indicates. Of course, it is always in the phase of improvement, the development. We take more data, ML based machine learning. So you ingest more data and you make the model more stable, and more calibration can be done on those models. So we always have a problem in the industry while drilling. You get a the cracks in the tools or fatigues, or you get a twist offs in the motors, or you get some of the major dents happening on the RSS when we are rotating at a very high speed. So this model will give you the safe drilling window. It will enhance your drilling stability so that you can save everything right from the bit to the top drive. At least some contribution can be done to minimize those problems, because you drill through the different types of the formations, and you have a different weight on bit and different RPM capabilities for represent to the different type of the formations. So that is the ROP optimization, which will help you in defining the safe drilling windows. Second one is about the torque and drag and the friction factor deconvolution. Like we know the torque and drag is available. Torque, you monitor the torque on the rig site and also on the in the some real-time operation centers. But this model will help you in doing the torque and drag analysis while drilling. Along with it can do with the reaming, reaming in, reaming out, I mean back reaming and washing up, washing down. Also, you can do some kind of calibrations so that you can adjust the friction factor so that you will minimize the unstable borehole conditions. And the friction factor deconvolution is like a triangle formation in between your inclination, azimuth and hole cleaning. So it will indicate what is the problem in the hole, like you have the hole cleaning problem, or you have inclination or high dog legs. Because of that, you are facing the problems while drilling or while tripping. So these are like those engineering supports for the problem. Then again, we have the science-based models, which, as I mentioned about the bit wear prediction, that when you run the bit, it will estimate and predict based on the type of the formation available, that how long the bit will survive. So because bit involves, if the bit damages or bit is not fully utilized, it will cost you the trips. So that will be like a big challenge to decide in case of the deep water, or of course on the shallow water as well. The offshore, everything is like very costly. So doing the bit trip is like a 24 hours or 36 hours of trip, which is in the deep water. It is very, very expensive. So it helps the bit wear prediction to help like when can you change the bit. It includes the cost also, like how much cost, if you optimize the parameter, how much cost you can save it for the bit cost. That is also predicted with this model. And of course, we are doing the worldwide pilot project to enhance and calibrate more with those based on the ML and AI technology. We have something which is early kick and loss prediction, which is based on your return flow, that it helps you to eliminate the use of the Coriolis effects. Like we have the EKD type of the equipments. This model will help you to eliminate that, and you get direct results from the flow line, whether you can stop that kick or loss. Of course, it is again based on the accuracy of the equipments. Like if the equipments are good, it will help you in predicting those in a little bit of advance, not in very advanced, because if you don't drill that formation and don't get a losses, you will not predict. It will only predict when you see there is a reduction in flow and all. So the computation will goes to the models, and it is also supported by the alerts. So you define the thresholds, min max for that either flow or either weight on bit, RPM, and it will give you the alert with showing that, okay, the friction factor is high, or your the pressure is dropped down than the calibrated pressure. So it gives you the pop-ups which helps you to interpret where exactly to see on the model, rather than searching that where I should interpret, where is the problem, where it might take you 30 minutes to identify the problem. But these systems keeps on giving the alerts. So the realistic alerts, there are some of the false alerts also. So you have to give the scale properly so that you can actually predict, and you can stop that incidence. And along with that, we are also supporting with some of the actionable incident report capturing. So if you see the incident, if the incident happened somewhere while drilling, and you want to take a capture and you want to express that and send it to someone that this is the problem, you can take a capture and you add a couple of words in that, and rest everything will be in the annotations, and the profile it will show that this is the problem happened, and you can circulate very easily to the rig, to the drilling engineers, to the drilling managers, to take an early decision, and not to spend more time on decision making or thinking that what exactly has happened. So that is the help of that EKD and report generations. Regarding the stuck pipe, we have some of the I'll go to the first to the stuck pipe. So this is the model which will give you some of the probabilistic assumptions and the predictions based on the readings, right? So one is the left color red sign, which is I'm showing. It's about the differential stuck. So differential stuck is not a very common phenomena. It might happen like a 20% out of the 100%, and it happens with the static conditions mainly. Either you are doing the connections, or if you are doing the tripping in and tripping out, and you are static, you are having the overbalance conditions above the mud weight, or your pore pressure is getting really low, and you are getting the indicators like a breakout torque is increasing and all. So, but with this chart, it will show you the probability of 0 to 100%, how much is the potential of getting stuck, and that is differentially. So, because in the back end, there is a mathematical model always operating, and this will help you to interpret that if it is going beyond 60% or 80%, it is going to get stuck. So you have to stop it over there. You have to do some changes. Either you have to optimize the mud weight, either you have to do the tripping faster, or reduce the connection times. So all those things will help you with this model. And this is right now it's available with the drilling, tripping in and tripping out. The second model is about the casing runnability. So basically, the name signifies that it's a casing which is show the behavior of the runnability. But this model is prepared in such a way that while drilling itself, it will show you the borehole condition, whether the borehole is good or not, and that if you put your casing in place at that point, how the casing will behave. If the casing will be still go without any problems, or casing will face the problems. Because casing might face the problems because you cannot rotate the casing. I mean, unless you have the casing while drilling, but you cannot rotate the casing. So you can only pick up and slack off those casings. And if you have a ledges, if you have the high dog legs, whether that casing can go or not, this will show during the time of the drilling itself. So if it is showing during the drilling that the condition is still worse, so what you do, you take your decisions of back reaming, wash up, wash down, you condition the mud, or you do the multiple reciprocation before you making the connection. So that is what the predictability is shown at that point. But of course, if it is a very much time bound, then it still gives a problem. So that is at least if you have like a development well drillings, you should not face this problem if you do the good hole improvement at that point. So that is the casing runnability condition this model shows you. Second model is about, if you see, this is about the vibration charts. So as I mentioned, the safe drilling window, the bottom one is showing is as a green window. That is your safe drilling envelope. That includes your in between your lateral and torsional vibration and the ROP line. And there is a one more line which is going is like one is the critical speed and one is the hole clearing line. So in between that, you try to fix your drilling window so that predicted to be a probabilistic way of having the better drilling approach without having the lot of vibrations, and you can drill safely. So that is what is model predict. But again, of course, like we have more calibrations because the different clients or different areas have the different compressive strength of the formation. They have the different stresses with the formation. So when we get more and more data, the model will be more calibrated and stabilized. So that is how the model is developed, and it is still in the phase of more development. And in the left side, we get the optimized window, which is which shows you like, okay, I'm using this flow rate, RPM, and weight on bit, so that I will, if I'm using that, this will give the window that you can still enhance or still you can reduce, so that you can get a better drilling results. So that is what this ROP optimization is used for. Yeah, so these are a couple of examples which I have shown. Of course, the bit prediction, I have not shown the complete results, but in like we have across the globe, we have more successful runs. We are more calibrating on the harder formations. We haven't tested yet on the granite and those basaltic type of the rocks, but in the near future, we will also do that. We have tested with very high abrasive sandstones and some of the dolomitic limestones. So those are also, I mean, we have used in Aramco and other clients over there. And we are still calibrating the models better, so to deliver the better results. And this is the roadmap of the further what we are going to do with RTV is that, as I mentioned, automatic report generation. So user need not to spend more time on the making the reports. He can get the some of the good snapshots with the problems indicators, and he can write down the couple of lines, and he can generate a report. And with his end of well report also, he can keep at, adding those and then submitting to the client or user, whoever wants the immediate report of that well, what happens with that well. Event mapping is one thing which we are doing is like when you have an offset well, some event happen, like you have a stuck pipe, you have a losses, you have twist offs and all. So those events are captured, and those from the offset well, it will be injected to the current well, so that before drilling the well, while planning itself, he will have all the events, risk, and its mitigation method ready before he can encounter those problems. So that is what is about event mapping. We have some multi-well analysis with the RTV, which is like a streaming analytics and KPIs. We can compare the different wells ROP, their invisible loss times, non-productive time, and also some of the tripping and drilling performances that can be tracked. Apart from that, we have upcoming models which are coming for the mechanical stick and the jar placement. So we have like a cutting bed accumulation, plug friction factor, which is for the trip out. We have differential stick, casing runnability, pack off module while drilling. And we are adding more into the mechanical stick issues, which is like a wellbore geometry related. And one more thing is the jar placement. Like we have an optimal jar placement, and if you are getting stuck or if you get stuck, what is the methods you can use for the jar that can be shown in advance rather than getting a full stuck. Because you will always see the problems, right? While back reaming and all, you will always see that, okay, it is going to get stuck. So probability will be given by the model, and what needs to be done in the next, it will be also going to be delivered by that model. And also we are doing some enhancement with the well schematics, which is like we have a dog leg. We are going to put it on the well schematics, where will be the packers can be placed, which is the best possible positions and all. So that is also, we are trying to put it in the visualization. So this visualization will help user or client to determine like where we can place optimum placement of those completion tools and all. So that is what we are also doing in that one. So this is the enhancement we are going to do with this model. So this is about one particular model, real-time well engineering.